Yeah, thank you very much. Thank you very much for the adapter. It is a pleasure for me to be here. I think I will wait 1 more minute until everybody's seated, and then I think I will start. Okay. Yeah, as the introduction is, my name is Bruno. I'm going to talk today about efficient computer vision on edge devices, or how we at biped build an AI copilot to guide blind and visually impaired people. Yeah. As seen before, as I told you, my name is Bruno. I'm the CTO and co-founder of biped. My other co-founder is sitting there. I'm originally from Germany. I have a master's degree in computer science, and funny thing is, there seem to be quite a few other Bruno Vollmers on Twitter, so if you want to reach out, watch out, the 5 is necessary, otherwise you reach some random people. Okay, what is biped? Biped is a solution for blind and visually impaired people that you wear over the shoulders. It can detect, track, and predict the trajectories of all obstacles and objects around you and help you avoid obstacles. The way it does it is it analyzes the environment, and then it gives you 3D audio feedback, which you hear via a pair of bone conduction headphones, and then you have the chance to see what's happening around, or hear what is happening around you, and then navigate accordingly. The whole system consists of 2 parts. The first part is the harness that is worn over the shoulders. It consists of a camera unit on the right, a computation unit on the left, and a battery in the back, and the bone conduction headphones, which allow you to hear what is happening in the environment with the addition of our 3D audio feedback. Here we have a little demo where you can see some blind users testing previous devices, previous prototypes. They can avoid obstacles. They can understand their environment so that they can find, for example, in this case, people. And it makes it very intuitive to not walk into obstacles anymore. We've tested it, as you can see, in many different environments, and so far the feedback has been overall very positive. So how does it work internally? Basically, our AI copilot consists of 4 different steps. In a first step, we use interior sense cameras to acquire images as well as depth information of the environment. In a second step, we then take those images and in parallel do what we call obstacle detection to detect generic obstacles as well as object detection, which is probably a task most of you know. Within the object detection task, we also do tracking and estimation. In a third step, we have a prioritization step, which is needed because we usually detect way more things in your environment that we can tell you at the same time about. So we analyze the environment and only tell you about the things that are actually important for you. As a little example, when you walk down a sidewalk and there are some cars parked, right, you might not be as interested into the cars as in the bicycle that is coming towards you. And then finally, in a fourth step, we take this prioritized input and with the help of HRTFs, generate the 3D audio feedback that you hear on your bone conduction headphones. And I think the most important part here is that all this computation, everything from acquiring the images to actually giving you feedback, is computed locally on an embedded device, which in our case is a CADAS VIM3 board. And then on the side, to make the using of the device easier, you can also always connect with our app to the device via Bluetooth to change settings, customize it to your specific needs, or start and stop the pipeline. And so, I mean, as I said in the beginning, we talk about efficiency and why efficiency is important. And the first thing, or the question I always receive at this point is like, if you really want to have something efficient, why do you use Python, right? Why don't you go for something that is made for super quick computation? And the reason we prefer Python at biped is that it just allows us to iterate really fast on features. It allows us to develop stuff really fast and try out different things, while I think with other with other languages that would take longer. And then the second question I get is, okay, why don't you just accept that it's slow? And the point here is, what we don't want is that we develop a feature which takes so long to compute in initial computation that we can actually not use it, right? So as an example, if the whole local computation takes more than 2 seconds, and then we have some time to play the sound, once the user reacts, he is probably already bumped into whatever is in front of him. And so the reason is, on one side, we want Python for its ability of fast iteration, but then on the other side, we need an efficient, optimized algorithm to actually be able to test the features that we develop. And that's basically why we want this pipeline to run in roughly something below half a second, so that with playing the sound, the user has time to react within a second to a new obstacle or object appearing in their field of view. And so in this talk, I'm going to talk mostly about how to find bottlenecks in your algorithm, how to optimize the algorithm towards a better runtime, how to optimize the code, and some additional tricks on the side. I know there are many other options here, which I'm not going to cover, so this is not a talk about how you can use other programming languages or how you can use GPU-related optimization techniques. And as a little disclaimer, I'm also only going to touch, because we have only 25 minutes, only going to touch the overall high-level views on all these things. Okay. To make it a bit easier for you guys to follow, I'm just going to introduce a little task where we've done the process that I'm going to introduce at biped, and I think that gives it a bit more a visual example to follow along with the techniques we're going to show. The task that we picked is called floor segmentation, and what it basically does is we have an input image, and we want to know which parts of the input image are actually ground that the user stands on. And we use that internally in our pipeline to detect obstacles and holes in the ground to tell the user about facts like, just in front of you, I would not recommend to go further because you're going to have a problem there. And this is quite obviously a task where real-time feedback matters a lot, because when people walk and you are too late with the feedback, they're probably going to bump into something. And the first thing that usually comes to mind when I talk about segmentation is a deep learning approach. The problem really here is that for two reasons we cannot use deep learning. One, we have a very limited computational budget when it comes to deep learning, which we already use for the object detection model. And two, segmentation approaches are usually quite slow. And we need something, as I mentioned, something fast here. So we implemented our own little algorithm. If we have a look at this example here, on the left you can see the original sequence that we recorded next to in a metro station next to our office. And then in the middle you can see what we implemented like without any optimization, and as you can see, it's barely usable, right? It's not something where the feedback would be valuable to the rest of the pipeline. And then on the right, you can see after we applied some optimization steps, it runs quite a lot faster. And so this is something which is not the perfect state of it, but it's good enough that we can actually evaluate if the feature that we developed there is useful for something, or if we want to invest more time in making it robust and properly fast. So how does that work internally? Quick introduction. What we do is we take the input depth image and we divide it into a group of superpixels, where each superpixel represents a group of single pixels. We then take these superpixels and compute the normal, which stands on top of the superpixel with a technique called principal component analysis, and then take the normal of each superpixel and combine it with a region growing approach where we compare those normals against each other to see, okay, which of the neighboring superpixel have similar normals to assume, okay, they seem to be on the same plane. And then we grow the region to find different planes in the input image. And then we can, with a few simple tricks, can assume, okay, this is the biggest plane. That seems to be the plane that's connected to the bottom. Okay, that seems to be the plane the user stands on. In a very first step, what we always do at biped and what I would recommend to everybody is before you do any optimization step, you actually have to find out what are the problems or what are the slow parts in your algorithm. And even though you seem to have a feeling, and I've had that feeling many times as well, I would still do that step, invest the time just to be sure that you don't work on the wrong part. Here, a very simple example from Amdahl's law. And basically, there you can see, imagine you have any kind of algorithm. It's split into two parts, A and B, red and blue. And what we can clearly see here is if we put a lot of effort into optimizing the wrong part, the output would actually be less influential on the overall result than if we just put a little bit of effort into the right part. And that's the point here, is that really a first step in any optimization procedure within wherever you work with this should be finding out and profiling what actually the slow part is. A very simple way to do this is timit decorators, or like functions that just time the runtime. They're quite simple to use, but really not suited for larger projects, as they don't give you really a detailed feedback, and they're quite hard to implement. So what would we use instead? I would recommend to use a profiler. There are quite a few profilers integrated into the standard library of Python, and the one we use is cprofile, as it is super easy to use. There is different ways you can use it. So at the top you see an example where you just wrap the part of the code that you're interested in, or at the bottom you can even profile a whole script. And it gives you a very detailed feedback on where the times run. Here we see an example of the profiling output of cprofile on our simple implementation, which I showed you, where I showed you the output in the beginning. And obviously, that's quite hard to read, right? If you know what you're looking for, it's still possible to use, but anybody that starts working with this has problems to read this. And so if you combine it with other tools, in our case, SnakeWidth, you get a proper visualization of the data I just showed you. And it's a lot easier to understand where time is spent. And in our case, we see that the PCA computation is actually the majority of the computation time. And so in our little example here, based on that information, we decide to spend most of the optimization time within the PCA computation. And before I would touch any code, what I would always look at is first the algorithm in itself, because the chances are very high that when you develop something yourself in a first iteration, you have not considered all the edge cases, you have not considered the best way to do it. So what I would first have a look at is, can we take our algorithm and find some ways to optimize the algorithm? This is obviously something that is highly individual to the algorithm you're working on, but there are some ideas I would say I can give you now which make sense, so to speak, so which most of the times work well. The first one is when you do some computations in your algorithm, and they're like the full exact computation, is there any way you can approximate that computation? So to speak, that you don't have to do, it will give you a similar result, but you just have to run it for a bit less, like a less costly computation. And the second thing is, when you go through your algorithms, can you somehow introduce conditions that simplify the process in some case? So can you rule out edge cases where you don't have to go through the whole algorithm at once? And if you look at our PCA computation, the things that we can make to run it faster is basically pretty simple. In the beginning, I said we take all the points that are within a superpixel to compute the PCA. And what we found out over time is that you can also just take a subset of the points. You would receive a very similar normal, but the computation is way less intensive. And the second idea, in our case, would be that there are some invalid superpixels which are quite easy to find. And we just have to find the right conditions to rule them out, so we don't have to do any PCA computation for them at all. Here, a visual example, what I mean by sampling. In our case, when you look at, for example, this example with all the pixels, it works equally fine if we just sample 20% of the pixels, take those to do the PCA computation, but we have only a fifth of the computation time. And what we saw is that this already led to a huge increase in, like, a decrease in runtime and increase in, like, the frames we can process per second. And this is, I feel, like a really good example to show you that sometimes it doesn't need to be something within the code or something, but it can also just be your algorithmic design where you can have like huge potential to increase the speed. And then the second example would be on the right. You see an example input of like the whole division into superpixels, and you can see, for example, these black areas, which are invalid pixels where the hardware, so the cameras did not, were not able to get a proper valid value. And if a superpixel consists mostly of these black values, we are not really interested into that. Or if there's too much depth variation within a superpixel, that would show us there's most likely not going to be any plane because it's too noisy. And so these two we can just kick out directly and not do any PCA computation at all. And that already gives us another boost. The boost in this case is smaller because this doesn't happen too often in an average input. Just to summarize here, what we do now is we go over all the superpixels, we check our two conditions. If they are not the case, then we sample this original superpixel and then only compute the normal on the subsampled set. And then when we've done that for all the superpixels, we perform region growing and then select the ground plane we're actually standing on. So now that we've found out what is the slow part, we had a look at our algorithm, the next step would be, okay, how can we actually look at the code itself without changing any more logic and make that run faster? And I mean, the first choice is going to be quite obvious, and I really hope most of you already know this library. If you work with vector matrix data, any kind of number data in bigger quantities, NumPy should be your go-to choice for any kind of computation. The reason why is that a lot of very smart people have spent a lot of time trying to figure out how to make that run fast and easy for you to use. And under the hood, it basically vectorizes operations and stores the data in continuous chunks of memory, which makes it a lot faster to actually work on that. And just to enforce that point here, I'm just going to give you a simple example. So we have this very simple example where we take any kind of vector, and then we compute the square norm. And what we see is when we take a quite huge vector like this with 1 million entries, that it takes quite some time to do with a basic Python for loop. And if we take the same computation, but we implement it with NumPy, you can see that by a quite big factor, the computation time is decreased without losing any readability. I feel like the bottom one might even be easier to read. And so there's not really any reason not to go with NumPy if you can. So once we've integrated NumPy, the next step, if we feel like it's still too slow, would be to work, for example, with something like Cython. There's other libraries which do the same thing. For us, we found Cython works the best, but there is other libraries like Numba out there which you can use as well. Cython is a superset of Python, which converts type-annotated Python into a compiled extension module, and it does that not at runtime. So when you actually use that code, it's compiled to something that is a lot more efficient to run. And this is especially useful if you, for whatever reason, cannot stop using for loops and want to get the most out of your mathematical operations. And usually it works quite well with NumPy. Little warning here, you should read up on this a bit, because there are some cases where you can actually make the runtime longer if you use it together in a wrong way, but it's quite easy to understand. And just to give you a little example here, within our pipeline there is one position where we just convert quite often coordinates from one coordinate system in the other. And if we implement that in Python, and then we take the same one and implement that in Cython, we can see the boost is not as much as we had it before with NumPy, but it's still by quite a significant margin, especially if we think about the fact that we use that a lot. Okay. Now that we've had, we looked at how we use, how we look at the profiling, we looked at the algorithm. Everything so far has still been sequential, and I think everybody that has worked with a computer is aware that our computer does not consist of only one processor, and is aware of what the terms multiprocessing or multithreading stand for. And so the question that naturally comes now is, okay, the PCA computation, it doesn't really matter for the 15th superpixel how the normal of the first one looked. So we could really just do that in parallel. And so, as I mentioned before, the terms that should come to your mind now are multithreading and multiprocessing that do offer, in general, the possibility to parallelize computations. The problem really here is, and that's the one pitfall I just want to point out to, that threads are not really an option in Python due to something called the global interpreter lock. I think they want to change that in future versions of Python, but currently that's something to look out for. The problem really here is that when you run threads, you still only have one Python interpreter and one memory space. And even though you have multiple threads, the thing is that only one thread at a time can communicate with that Python interpreter. And so the thing what seems to be parallelized is actually under the hood not parallelized. And so that's something to keep in mind. And if we want to actually reach true, so to speak, parallelism, what we have to do is do something like multiprocessing, because in this scenario, you have multiple Python interpreters, and this is the important part for the next slide, multiple memory spaces. And so now what we can do is use the true potential of our machine by looking at by parallelizing the computation that does not really belong to each other or just does not need the information of the others, and like really get the most out of our machine. And just to say, there is a reason there is multi-threading, right? It's just for other things. In our case, it doesn't really work really well, but it doesn't mean that there is not something you can use it for. And as I mentioned before, we now have that problem where we have multiple memory spaces, and even though they do not really need the information of the other PCA computation, we still need the result and need to transport that to the main process, and we need to put the image data into the new process to actually do the computation there. And the first thing that comes to mind is queues. The problem really with queues is that when you use queues between different memory spaces, there is a few, I would say, unnecessary copy operations, which is not really a problem if you use very small data, like you would pass some strings or, I don't know, a message. But if you use something, for example, in this case, which is quite big, which is an image, like an RGB image of 1,000 by 1,000 pixels, and you copy that 1,000 times, you can really see that queues on the left, they take quite a long time just for moving the data from A to B. And because in Python 3.8, there was a module introduced which goes around this, which is shared memory, right? It's natively integrated from Python 3.8 on, and it makes it very easy to actually access shared memory and pass data around in systems with multiple processors. And the point I just want to make here, if you have bigger data, use it. It's easy to use. It makes a lot of sense. You just have to copy it once to the position. For example, in our case, what we do is we take the whole superpixels, we copy it once into shared memory, and then all the processes that want to, they just need the index in that data, and then they can copy out their data that they need, and there's not the need for like multiple big copy operations when you pass the whole image into a queue, and so on. Here we have a little demo of how that internally looks like once we use the car. Unfortunately, we do not have audio right now. Otherwise, I could also play you the audio. If anybody's interested how that sounds internally, I would ask me, go on our website. There are some examples, and I'm happy to show you some stuff. And just the summary here, the things you want, you should keep from this talk is, the very biggest thing is profile first. Don't do it afterwards. Do it directly. You're surely working on the right thing. And then in combination with that, visualize and track the performance throughout the whole process so that you know you're not over-optimizing stuff. You're not doing something that actually makes the performance worse. Then, when it's possible, improve algorithms and use existing libraries that are optimized for this, and do not do stuff yourself. You can use a library that actually has already done it. And then the last thing is, if you want to write fast Python, do not use for loops. That is everything. I hope everything was clear, and I'm happy to answer questions.
Thank you so much for the amazing talk.
Thank you very
so
much.
We have quite a number of questions for you. I think about 6 questions. Yeah. So the first question, I think you already addressed that. What does audio feedback sound like?
Yeah, I'm happy to show that we do not have audio right now, but the way you can imagine it is we give different objects in your environment, different types of sounds, and then we use these, as I called HRTFs, to give them a directionality. So you would, as a simple example, let's say clap would be the sound for a car, and then you would hear it, in this example you saw, move past you, and then we use different techniques to also give it an understandable distance. So for example, it would get a bit more quiet, and the sound would be played less over time.
All right. The second question, does the software detect holes or really low obstacles?
Sorry?
Does the software detect holes or really low obstacles?
I mean, yeah, so the thing we're working on, and the main reason we're doing floor segmentation, is to detect holes and generic obstacles, so to speak. I mean, the main reason why we do obstacle detection in that sense is that we cannot really rely on the object detector to find all the objects all the time, to know all the variations of an object. So the main idea really here is to say, we have this obstacle detection as the main source as like a backup system, and then if we have additional information by the object detector, we use that, but the obstacle detection is always there to detect all problems around you.
Thank you. The next question. Some companies believe we can use standard cameras in place of LiDARs and 3D cameras. What's your take on this?
So in our case, we use not LiDAR, but infrared sensor within our stereo camera setup. So the way it works is, I don't know if you can see that here. Yeah, I'm having it. So in the end, what you see here is we have a stereo camera setup with a LiDAR sensor in the middle. I think, I mean, what you refer to most likely is to Tesla, and Tesla using just visual input and without any other thing. I do not. I think this can work. I mean, obviously, in Tesla's case, it seems to work at least a little bit. In our case, really the problem is that good depth estimation models are super costly to compute, and we really don't have the space to do that. So that's why we have to rely on something else. And most LiDAR sensors that we have seen so far that are like easy to integrate into a product like this are too big, and that's why we rely on infrared.
All right. For the next question, doing the filtering of the superpixels will also take some time. How does that affect the total time optimization? Should I go again?
I think.
Should I go again, or did you get that?
No, I think I just have to repeat it, please.
Okay. So doing the filtering of the superpixels will also take some time. How does that affect the total time optimization?
You have to read the question.
Oh,
sorry.
all right.
Yeah, or yes.
Yes, you were mentioning that you did some of the superpixels.
Yes.
Because that, of course, takes a little bit of time, right? You have to go through the pixels.
Yes.
And some of them. How does that, when you show the total reduced time of this operation, how does that affect?
I mean, it doesn't really have a very strong effect, and it really depends on the scenario where we're in, right? If, for example, we have something where like a lot of like noise is within the environment, and the depth camera and the depth sensor has a lot of problems picking stuff up. There's more invalid stuff, and so more this happens. In general, I would say we only discard a few superpixels per image, per run. But you can see, I mean, we measured that, and we saw that running the checks is always, like, once we discard 2, it's already worth it. By not a huge margin, but it's already worth it. Because, I mean, in the end, it's just, the one is just counting the number of zeros in an array, which is super fast in NumPy. And then the other one is just, you check how far the values spread. And that's also quite easy to compute in NumPy, and then you can just do a quick check there. The PCA computation is quite hard. It's always like, if you can reduce that, it always makes sense.
All right. We have less than 1 minute for 4 more questions.
I mean, I can answer questions afterwards.
All right,
we
great,
do one
great.
more and then.
Okay, so are you guys hiring?
We are hiring.
Okay, great. Is the
Go on our website, I would say, and then, I mean, a little side note, we're from Switzerland, so that would be, I mean, it's beautiful there. I would highly recommend moving there. I can show you some pictures of the office later, which is a nice view, but yes, please reach out. We are always looking for people.
For the rest of the questions, I think you could always ask on Discord.
Or write me on Twitter or an email. I think that's something that works well. And I'm also here until Sunday.
All right, great. Thank you very much, Vollmer.